Alright, this section is on solving trig equations, and there's lots of different types of trig equations we can see, so if you are really rusty, you might go back and look in pre-calc when that topic was studied, all the different types of equations you can have and really get into those. It will not benefit you to tough out this section and not understand it and just assume that you checked it off so you're okay, because trig shows up a lot in calculus. It kind of shows up in the calculus the same way that factoring shows up after you learn how to factor. Like, you learn it first and then it starts to show up everywhere and they just kind of assume that you know how to do it. And if you're uncomfortable with it, then you're uncomfortable a lot at first. Same thing with trig. We don't have like dedicated trig days. It's just like trig problems show up pretty frequently and the assumption is you can work with them. So if you allow yourself to be frustrated by them or not really understand them, then that's going to be something that's going to go on for a long time before you are forced to get comfortable with them. So you might as well work on it now. All right, that was just my 2 cents. So we're going to go ahead and solve these equations. And when you solve a trig equation, you have 2 options. You can solve for all possible solutions, or you can solve for solutions on a given interval. And so I'm going to say we're going to do all solutions for one answer. And then for our second answer, we're going to do the solutions from 0 to 2 pi, and then just know that that's something you have to consider when you do these problems throughout the year. So I'm going to say all solutions and from 0 to 2 pi, and I'll specify both of those answers. So the first equation that we're going to solve is sine squared x equals sine x. And this is kind of like if you were solving the quadratic equation x squared equals x. I'll write it right here, x squared equals x. This, it's a quadratic equation. It's going to have multiple answers. So if we were solving this equation, we know that when we have quadratics, we need to set them equal to 0, and we need to factor. And if I was to factor this one, that would be factoring out a GCF of x. And then that would leave me with x minus 1 equals 0. And I would have 2 solutions. I would say this one is x equals 0, this one is x equals 1. All right, so similar idea over here. We're going to say sine squared x minus sine x equals 0. We're going to factor out a GCF of sine x and then leave sine x minus 1 behind. And then sine x equals 0 and sine x equals 1. All right, now this problem was done. That's not actually the problem we were doing. We were doing this one. This one is not done yet. Now I have to think about, on the unit circle, where is there a y-coordinate of 0? So you can get out your unit circle. This is no longer inverse trig functions where we're looking at specific quadrants. Now I am the one doing the inverse trig, so it doesn't have to be a function. This is kind of the idea of like when I am the one taking the square root, I have to put a plus minus in it. So when I am the one doing the inverse operation, that means I have to look at the entire unit circle. And on the entire unit circle, you can see that a y-coordinate of 0 happens in 2 places. It happens at 0 or 2 pi. You can say either of those, 0 or 2 pi. And it also happens at pi. And then I have to look and see where a y-coordinate is positive 1. That only happens in 1 place, and that's at pi halves. The other place you might be tempted to look at is 3 pi halves, but that's actually a y-coordinate of negative 1. Okay, so those are all the answers we have. Now I have to think about how I'm going to write these solutions if my option is that I have all solutions. So for this answer, I can see I've got 0 pi and 2 pi, and if I were to continue the pattern, it would just be all the multiples of pi. So I would say x equals 0 plus pi k. And I'm doing that because I can see that all the multiples of pi are being used. For the other answer, it would be pi halves. And then typically with sine and cosine, the answers repeat for every like coterminal angle. So I would have to add a full circle to get the next answer and then another full circle. So I'm going to say plus 2 pi k. All right? If I'm writing the answers from 0 to 2 pi, then that means I can include 0 and I cannot include 2 pi. So I'm going to say 0 and pi. I'm not going to write 2 pi, and then I'm going to write pi halves. So the answers are related, but they're not identical. All right. Example 2. Sine x equals cos x. There is a way to solve this equation with using trig identities and actually getting the sides to be the same and maybe setting it equal to 0 and maybe factoring. It's a lot easier to think of this problem intuitively. So if I can picture the unit circle and think about where sine, which is the y-coordinate, is the same as cos, which is the x-coordinate, then that happens in 2 places. It happens at pi fourths. The answers are root 2 over 2 and root 2 over 2. And it happens at 3 pi fourths. Nope. It happens at 5 pi fourths. And that's where they're at negative root 2 over 2 and negative root 2 over 2. So I'm going to say they're the same at pi fourths and 5 pi fourths. So if I was to write my all solutions answer, I have 2 ways I could write this. I could say pi fourths plus 2 pi k, 5 pi fourths plus 2 pi k, but these are exactly opposite of each other on the unit circle, which means they're pi apart from each other. And so really when I write the all solutions answer, I should be writing pi fourths plus pi k. That's like the most simple way I can write it. And then for my answer from 0 to 2 pi, I'll write just pi fourths and 5 pi fourths. Now, I would say I can't really think of a situation where it would mess you up to write the all solutions answer as differently than that. The important part is that you are able to find the different solutions, because in calculus we wouldn't just solve the equation, we would have a purpose for solving it and we would want to use those answers for something else. So the most important thing is that you can figure out that pi fourths and 5 pi fourths are the 2 numbers, and that you could continue the pattern if you needed to find more answers. But as far as like writing the all solutions answer perfectly, it's okay if that is not your strongest suit for calculus. All right, third problem, we're going to do 2 cos squared x plus sine x minus 1 equals 0. So this looks like a quadratic, but it's got a mixture. It's got kind of like a variable as a cos and a variable as a sine, and that's not helpful to have both of those in one problem, because it's kind of like solving a quadratic where you have like a y squared and then a plain x. You like can't do anything with that. So if we look at our trig identities, we know that cos squared is the same as 1 minus sine squared. So if I can take the cos squared in the problem and replace it with this, then my entire problem will be in terms of sine, and that's much easier to deal with. So I'm going to take this cos squared right here, and I'm going to replace it with 1 minus sine squared. And then I'm going to go ahead and distribute that too. So 2 minus 2 sine squared plus sine x minus 1. And I can kind of recognize that this is another quadratic. It's kind of like having 2 minus 2x squared plus x minus 1. And if I was doing this problem, I probably would not want the squared term to be negative. It's just easier to factor when they're not. So I'm going to go ahead and take everything on the left side of the equation. I'm just going to move it over to the right side of the equation. So I'm going to add the 2 sine squared to the right side. I'm going to subtract the sine x over to the right side. And then a 2 and a negative 1 means that on the left side I have a positive 1. So when I move it over to the right side, I have a negative 1. So what I'm thinking about right now is I've got 0 equals 2x squared minus x minus 1. That's what I'm thinking about factoring. And when I factor this, this is a slide divide bottoms up problem because of the 2. So I'm going to think about what multiplies to negative 2 but adds to negative 1. And the numbers that multiply to negative 2 but add to negative 1 would be negative 2 and positive 1. So that would give me x minus 2 x plus 1. And then since I slid over a 2, I have to divide by 2. And so my two sets of parentheses would be x minus 1 and 2x plus 1. And then my solution would be x equals 1, x equals negative 1/2. Okay, so now I'm going to do that exact same thing, but over here with the signs. So I'm going to say that this would be sine x minus 2, sine x plus 1. I would have divided by 2, and I would simplify my parentheses and bottoms up. And so now I'm going to say, okay, my two solutions are sine x equals 1, sine x equals negative 1/2. And of course I'm not done. I'm going to scribble this out because this is a different problem. Of course I'm not done because I have sine x, not x. So now this is when I look back at the unit circle and I say, okay, where on the unit circle is the y coordinate 1? That was at pi halves. So I've got x equals pi halves. Where on the unit circle is the y coordinate negative 1, or negative 1/2. So I'm picturing on the unit circle where it goes down just a little bit, goes down just a little bit. That would be at 7 pi over 6 and 11 pi over 6. So if I'm looking for my all solutions answer, I'm going to have pi halves plus 2 pi k, 7 pi 6 plus 2 pi k, 11 pi 6 plus 2 pi k. That's my all solutions answer. And then my 0 to 2 pi answer is going to be pi halves, 7 pi 6, and 11 pi 6. Those are my solutions on the unit circle. Okay, so that's one type of problem you could be solving with trig, and that's those problems are kind of like, oh, I'm factoring a little bit to solve, and I would say the easiest way to do it if you get stuck is to like literally factor it off to the side and then rewrite the problem in terms of the trig functions, and that can be very helpful. All right. Another type of trig problem you can be solving are problems that have a period change, which means that how often that the number of their coterminal angles is going to change as well. So the answers won't repeat every pi k or every 2 pi k. The answers will repeat in a different pattern. So I'm going to go over a couple of these. So here, I can't just divide by 5 on both sides because that 5 is being protected by the tangent. So the first thing I need to do is do tan inverse on each side. Again, I am the one doing the tan inverse, and so this is not something where I look at a limited number of quadrants. I'm going to look at all 4 of them. So I'll go ahead and start off by doing tan inverse. And then what I'm going to do is I'm going to look at the unit circle and I'm going to say, where on the unit circle is there a y coordinate divided by an x coordinate that becomes this? So I know I'm not looking in quadrant 1 or quadrant 3 because those would be positive answers. So if I look at quadrant 2, I have to basically determine if it's this one or this one. Where would the y divided by x become root 3 over 3? So y divided by x here would be root 3 over 1, which is just root 3. So this is the one I'm looking at. So it's 5 pi 6. And then over here, same sort of idea. This is not the one I'm looking at because when you divide them, they're kind of simple. So it's 5 pi 6 and 11 pi 6. And tangent is kind of the special case because the answers really do repeat across the circle from each other. So when we do the tangent problems that have a period change, then we actually only have to set up one equation, not 2. So you can either do 5 pi 6 plus pi k or 11 pi 6 plus pi k, it doesn't matter. You'll get all the same answers. So I'm going to write 5 pi 6 plus pi k. And then I'll go ahead and solve for x, so I'm going to divide by 5, divide by 5. So x is going to equal 5 pi 6 divided by 5 is kind of like saying if you have 1/6 and you're dividing it by 5, it's kind of like saying I'm doing 1/6 and I'm multiplying it by 1/5. I want to know what 1/5 of that is. So this would actually be 5 pi divided by 30 plus pi k over 5, so plus pi fifths. So, and we can simplify that. I can say, oh, 5 over 30 is actually 1/6, so that'd be pi 6 plus pi fifths k. That's my all solutions answer. And then my answer, if I'm not doing all solutions, my answer if I'm looking for from 0 to 2 pi, then I have to think about my fractions and how those are working. So I would probably, if I was looking for the answers from 0 to 2 pi, I would probably leave this in terms of 30ths. And then I would say this is 5 pi 30ths plus, if I multiply by 6 on the top and the bottom, that would be 6 pi 30ths. So I would say if I'm doing my answers from 0 to 2 pi, I would say 5 30ths is my first, and plus 6, and then I'd get 11, plus 6 is 17, plus 6 is 23, plus 6 is 29, plus 6 is 35, plus 6 is 41. Gosh, there's so many here. Why did I do this? And if you guys recall from pre-calc, you would actually be expecting 10 answers. So then 47, 53, 59 would be the other ones. So that would be if you needed all the answers from 0 to 2 pi. To be honest, a 5x and these ones are probably not very common, but certainly a 2x, I would definitely see that in calculus. So understanding that the 5 changes how often you get your answers is important, and knowing how to find the other ones is also important, and being comfortable enough with fractions to be able to do it by hand is certainly a good thing. All right, number 5. Don't worry, guys. There's 9 examples. We're not done yet. All right, sine of 3x equals -1/2. So I'm going to look at the unit circle and I'm going to say, okay, I need to get rid of this sine, so I'm doing sine inverse. And so when I'm looking at the unit circle, I'm thinking, where on the unit circle is there a y-coordinate of -1/2? And that happens in 2 places. It happens at 7 pi 6, and it also happens at 11 pi 6. And this is not like tangent where the answers are across the circle from each other, so we really do have to set up 2 equations here. So I'm going to say plus 2 pi k plus 2 pi k. And then to solve for x, I'm going to divide by 3, divide by 3. So x equals 7 pi 18ths plus 2 pi thirds, okay, and 11 pi 18ths plus 2 pi thirds. Okay. So this would be my all solutions answer. And then if I wanted to look for my solutions from 0 to 2 pi, I would say, okay, let me multiply by 6 on top and bottom so I can have that common denominator of the 18. And then I would say 7 plus 12 plus another 12 plus another 12, 11 plus 12 plus another 12 plus another 12. And I would expect to have 6 answers. All right, so if those are confusing for you, this is as hard as it gets. Really, number 4 is a little bit overkill. They're not crazy common, but they certainly do show up, and students are very uncomfortable when they see them usually. So it's good to practice those so that you're not freaked out. Okay, the other problems I wanted to show you are problems where you do have to use a calculator to solve them, and so it's just a little bit helpful to remember the little shortcuts for how to find alternate answers, and so these are going to be quick. So here we're going to do sine x equals -0.38, and I'm just going to go ahead and write them all. Cos x equals 0.71, and tan x equals negative 1.34, and cosecant x equals 2.79. Okay, so the part that throws students off about these is that these are definitely calculator active problems, and if you were to do it in your calculator, you would get one solution, not two, and they're going for two solutions. So in the event that you forget how to do these in your calculator, I would graph the equation. I would graph the sin x function and then go into my calculator and put y2 as this number and then see, like I would basically cheat and I would use my calculator to solve an equation for me. But I'm going to show you how to do it, the right way so that you can kind of use that as a backup if you forget how to solve an equation. So this is in your packet. It's on page 23 if you need to look at the shortcuts. So here, if I'm trying to solve the sine equation, I just need to do sine inverse. And so this is the answer that most of you guys would get. You do the negative 0.389, you're good. The answer that a lot of people would not get is the second answer. And so for tangent, the shortcut is, for sine, the shortcut is you have to do pi minus the first answer, and then that is your second answer. Okay, so if I was doing all solutions, I would say negative 0.390 plus 2 pi k and 3.531 plus 2 pi k. If I was doing just the answers from 0 to 2 pi k, then I could keep the 3.531, but I could not keep this one because it's negative, so I'd have to go back up and find the coterminal answer for that, and that would be 5.893. Okay, for cos, I'm just going to do cos inverse 0.71. That's my first answer. And then for cos to find the next answer, we do 2 pi minus the first answer. So for this one, I would say 0.781 plus 2 pi k, 5.502 plus 2 pi k, and then if I was doing my answers just from 0 to 2 pi, I could say the 0.781, 5.502 are both good because they're both positive. Tan inverse tan inverse is the nice one because the answers repeat every pi, so you can do this one pretty easily. So for all solutions, I'm just going to say negative 0.929 followed by a 6 would be 30 plus pi k. There's my all solutions answer. For the answers from 0 to 2 pi, I would not write this one down because it's negative. Go ahead and add pi. So there is my first one. There's my second one. Okay. And then last, cosecant, I would not use this problem. I would say, let me rewrite it and call this sine x is 1 over 2.79. And then that is the problem I would do. So I would do, sine inverse of 1 divided by 2.79. And then I would write that down. So for all solutions, I would have 0.367 plus 2 pi k. And then for sine, my second answer is pi minus the first answer, 2.775. So that's if I needed to write all solutions. If I wanted the specific solutions from 0 to 2 pi, that's what they would be.